Hi, this is the last lecture of this topic. So lecture 11 will deal with the universal small signal diagram applicable for all PWM converters, non-isolated, isolated, operating in CCM or DCM. First, this is the summary of previous lecture. So last lecture recap. So this is the functional diagram of converter. So this can be buck converter, boost converter, buck boost converter by rotating this or any other converters derived from three basic converters, any other PWM converters. And this is the voltage feedback circuit. This is the modulator. This can be considered the large signal or DC model. So the use of this model is to explain the DC regulation characteristics of this structure, this negative feedback structure. So as we found in the previous lecture, if this condition is satisfied, the ratio of G2, magnitude of G2, evaluate at DC divided by magnitude of G1, evaluate at DC becomes infinity. For example, this is the finite value, this is the infinity. Then our voltage is always regulated at this value, which is related with reference voltage. This voltage is fixed, okay? So this is the G1 evaluate at DC. So when you want to change the output of your converter, so you change Rx, okay? So you change Rx, then you only change the output voltage without touching anything, any design of this voltage feedback circuit. So that is the one advantage of placing this output voltage controlling resistor at this point rather than any other point. Okay. So this is the equation for the output voltage, or simply this output voltage is divided by this and this, then that value times that division factor times this. It should become same as this because the virtual short property of this ideal op-amp. So this is the same expression, okay? But this is the easier to remember. All right. So this is about the DC characteristic of DC block diagram model of PWM converter, and this is the small signal model of PWM converter. We'll derive this, okay? It's not difficult, relatively easy to see this, okay? So this is what? This is the CCM PWM switch model, okay? And this is the simplified one, okay? So if converter is in DCM, you replace this with just the DCM PWM switch model. Now we are showing the CCM PWM switch model, okay? And this is the voltage feedback compensation. We need negative sign here always, okay? I forgot that. And this is a modulator gain. So you may use this, the linear gain, constant value, 1 over height of the lamp. That is fine if you understand the high frequency characteristic of describing function differentiation of modulator gain, then everything is okay. Okay? And the loop gain crossover frequency is way below the switching frequency, so that will be fine. All right. And this is the block diagram representation of this. This represents this input to output transfer function, under open loop condition, load current to output transfer function, and duty ratio to output transfer function. And this is the modulator gain, voltage feedback compensation. I need put negative sign here, okay? This is wrong. Then you have positive feedback, you are in big trouble. Then negative sign here, modulator gain, and this is duty ratio to output transfer function, okay? So this is the same representation. Why they are same? You derive these things to make them same, okay? For the CCM operation, you use this. For the DCM operation, you replace with the DCM PWM switch model and do the same thing. Then this can be considered as the universal block diagram representation of any PWM converters. Okay. So this lecture is relatively easy to follow, right? And after this, the lecture 8 is all done. So we complete the converter modeling. Then next one is we investigate the power stage dynamics. This is rather easy because we already have the small signal model, which is linear time invariant. Just the simple circuit analysis will show all the details of the power stage dynamics, and we can apply the frequency response concept, okay, and the Baudot technique. All right. One important topic is RHP0. Okay. RHP0 occurs all the PWM converters except Buck and Buck-derived isolated converters. Other than that, all the converter has RHP0. So this PWM converter is inherently non-minimum phase system, which is considered as a special case in the conventional control textbook. Okay, but the unconventional thing is the conventional thing in the power electronics. So we need to investigate the origin of that phenomena. RHP0 phenomena will be elaborate in this part, power stage dynamics. And after that, we'll discuss this voltage mode control of this all the PWM converters. Okay, so maybe this topic will consist of about 10 lectures, something like that. I'm not sure. So I'll be lecturing this topic in the next semester to my graduate student here in Gyeongbuk National University. And after each lecture or several lectures, I'll upload some edited version of video to this YouTube channel. Okay? Okay. So we'll move forward this details about this lecture 11. Now I'd like to discuss the AC characteristic of this system. So we are considering AC signal. Then for AC, this is shaded, and there are virtual short in between, and this is the AC ground. Okay, and there is a AC ground. This is a ground. There is a no current in between. So Rx is nothing. You can remove this for the AC signal. Okay, all right. And the node equation at this point is this is incoming current, and voltage here is 0. So we have this relationship, and you know this. This is the equation for the transfer function of inverting amplifier with minus sign in front. And this FVS is called voltage feedback compensation. All right. Without negative sign, just the ratio of two impedances is called voltage feedback compensation. And this, you know, this structure, this is the 2-pole 1-0. Okay. This create a pair of pole and 0. This also create a pair of pole and 0. And there is some DC integrated gain, combination of this plus this times this, you know this, okay? So we went through this many times, and this relationship between these parameters, okay? So we know everything, and small signal model of this, then we just replace this with PWM switch model or DCM PWM switch model, okay? Then that becomes the small signal model of entire converter. So it's shown here, okay? So this is entire converter, small signal model, that's a PWM switch model. With this arrangement, this is the buck converter, okay? But this one, this is shaded. It was the reference voltage shaded, so I replaced with this switch, okay? So I use the switch. I can use this line, but I use the switch, okay? And this voltage is 0, and this current is 0, okay? Because of this is the ideal op-amp, this is 0, then this entering current is 0, then this leaving current must be 0, okay? There is no current here, okay? So this can be opened, okay? Without changing anything, in terms of the AC characteristics, and this port is grounded. So this is ground. So we replaced this whole thing as this functional block, this voltage feedback compensation, FVS, and negative sign is here because it has negative sign here. That sign is moved here, okay? And this switch is open. This switch is open, okay? Then you remove this and you have this, okay? This is the small signal model of closed controlled PWM converter, and you further modify this in this form. And before that, just take a look at the power stage model, okay? This is the power stage model, and from this power stage model, you can easily derive transfer function from here to there, transfer function from here to there, and transfer function from here to there, okay? There are three power stage transfer functions of importance and of interest. This one, this one, this one, okay? You derive this, then you replace this, okay, with this functional block. So this is the same as this one, okay? Some students, they have question why this circuit model is the same as this block diagram. We derived this to make the both figures are the same, okay? Because of we derived this in this manner, and this functional block and this circuit diagram are exactly the same. That was our intention. So we derived in that way these three functional blocks of power stage, okay? And this is the definition of this power stage. This is linear system, so superposition principle is applied. So when evaluating this, the other two disturbance sources are deactivated, okay? And then this is the small signal model. You will see, okay? Later on, you will deal with this, to design your compensation, and to analyze the closed performance of converter. Just to forget about all the things, and this is the model you will use, okay? I have seen this for the first time. I was very confused. What is this? Where is the input? Where is the output? Everything is embedded here, okay? You don't have to this summing block. This block diagram representation, this plus, and this minus sign it contains all the information presented in the standard form, okay, with command signal 0, okay. So there are three important transfer functions here. Closed loop transfer functions. Loop gain is this one. Is the gain product of three functional blocks in the feedback path with minus sign in front of that, okay? So here is a one minus sign here in between, and we add this additional minus one, they cancel. So this loop gain carries all the information about stability, and in particular phase margin is very important. That can be used as the prime metric for the closed performance of converter. Okay, so that is very important. And the relationship between this input to output transfer function with feedback loop closed as this one, and output impedance, closed loop output impedance, transfer function from here to there with this is 0, this is grounded, and but this feedback loop is activated is this one. Okay, you can prove this easily. Some block diagram manipulation or Mason's gain rule. The simplest possible case of the Mason's gain rule is this one. Okay, know this. Okay, so this standard small signal block diagram is in this form. Okay, then how about the CCM and the DCM? So CCM has this small signal model. Okay, this is just the PWM switch model, CCM PWM switch model, simplified one. If you want, you add some resist parameter, and this is replaced with something else, but that is not necessary. Maybe that is okay for the simulation, but in the analytical derivation, get rid of that, okay? That simply make your job complicated without improving any accuracy of your result, okay? Just avoid that, that's fine, okay? And for the DCM, with this you derive this, okay? Then this becomes the general model for the ACCM PWM converter, all the PWM converters, including everything, isolated, non-isolated, with parasitic resistance. DCM, you use this one and derive this, okay? Then you have the same gain blocks for the DCM operation. The way of memorizing this is, this part is, it corresponds to the active switch, and this corresponds to this passive switch diode. Okay, so easy to remember, right? And this RI and RO, they are very important because it provides substantial damping for this, and all the characteristics of this. Okay, so this is the universal small signal block diagram for all the PWM converters. Okay. So this is the final form of small signal model of PWM converters. And I have this one example. This is PSIM example. This is the switch mode model for the loop gain evaluation based on the computational method. Okay. So this is the height of the lamp. Okay. Lamp height is 3.8, okay, and this is the voltage feedback compensation, and this is what? This is the setup to measure loop gain. This is the PSIM functional block, and with this AC switch command, I plot the loop gain with this red one, okay, red curve, and I plot the phase with red, okay. This is no. Oh, okay. This is the computational method. So it has some error here. Oh, something is wrong. This should be. Oh, this color is wrong. Okay. This should be the computational one. Okay, because some additional phase delay is coming up at high frequencies. So this should be computational one. Switch model, something is wrong, okay? And this is also switch model. So red one is switch model, okay? This is wrong, okay? So you understand this, right? Because with some noise is this one. This is the linear model. There is no noise. This is the what? Linear model. Okay, nothing is switching here. So this continuous curve is generated with small signal model for the loop gain measurement. So in place of this, you just added this. Okay, so this is the AC. This is a current, and current source is excited with this AC. Okay, this is the voltage, AC voltage is directly connected in between. You don't need this, okay? This is AC, and you are measuring this voltage here and here, which is loop gain, and this is same. The compensation remains the same, but this becomes just 1 divided by 3.8. This is what? Modulator gain, okay? This is the linear gain, so we cannot see any second order effect of PWM modulator, like the additional phase delay which showed up in this computational model, okay, something like that, right? But they are very good, okay. So up to this point, they are same, and if you increase this, then there is a phase difference is coming up, right? So placing the loop gain crossover frequency here to obtain the largest phase margin is not true, okay? actual phase margin is smaller than that. Okay, so this should be considered when you are designing compensation and evaluating the converter performance using this computational method. All right, and this is the final slide. I have three additional slides. Okay, I think we can finish in the regular class hour. Okay, so this is the universal representation of small signal model of all the converters in CCM or DCM. That depends on this. Okay, this is the transfer functions of the CCM. Then becomes a CCM model if they are from the DCM small signal model, power stage model. It becomes a DCM model. So this can be considered as the universal. Right? It's not really universal. You need to know this. Okay, three of them. Right? And three transfer closed loop transfer functions of interest. First one is loop gain. Okay, loop gain is simply product of this and this without this negative sign and this. Okay, and this is the Bode plot of transfer function, typical transfer function, and this is the polar plot of this transfer function. Okay, so here this is the 0 dB line of magnitude, and you take a look at the phase of your loop gain at this frequency and difference between this minus 180 and phase at that frequency as a phase margin. Okay, and this phase reduced to minus 180 here. Okay, then distance between 0 dB and magnitude at that frequency is gain margin. Okay, so this converter is stable with finite or reasonable phase margin and gain margin. Okay, the stability information is here. All right, and we used this polar plot of this loop gain. So at low frequencies, magnitude is very large, and the phase is minus 90 degree. So it starts from somewhere here and going like this. And at high frequencies, suppose this reduced to minus 270. This is not the case. Okay, this was a mistake. So it reduced to minus 270. Then this polar plot will slide along with this imaginary axis. Okay, so we defined this line segment A and this critical point B and the line segment C. So we conclude that when this crosses this minus real axis at some point, one point in line segment A, converter is stable. Okay, so this is stable case, and this unit circle and this angle is phase margin, which is same as this, and but this distance, this minus real axis cross frequency and this critical point, this distance is related with GM, proportional to GM. If this is long, length is long, GM is large. If this is short, GM is small. Okay, it is somehow related with this, actually inverse of something, but they are related with this. Okay, so with this information, you directly evaluate the phase margin, gain margin, and stability of converter by using this or using this. They are the same thing. Okay, same information with different format. Okay, and this one, this is audio susceptibility. Okay, this is the GBS, open loop input to output transfer function divided by 1 plus loop gain. You factor this out, then this is the numerator and this is the denominator. Thus, this is just the symbolic notation. Okay, then 1 plus TMS equals 0. Okay, denominator equals 0. It's the same thing. Okay, it's the same thing. Then this is called characteristic equation. Right? The root of characteristic equation is called poles and eigenvalues and natural models, and all the poles, all the roots are in This one, left side, left half plane of S plane, then stable. Okay. Otherwise, if there is a one near pole in the right half side, converter is unstable. This one is unstable. This should appear as the complex conjugate pair. Then there must be another pole. And if pole located at this imaginary axis, then another one should be there. Then this is what? Oscillator. Okay? This is unstable system. So all the information is here. Stability. For the stability, you can use this or you can use directly. Okay? Right? So this, they are all combined. So you should take a look at, or you should study all of them all together. They are closely related to each other. Okay? So that part is coming from the next semester. Okay, this is the end of everything. Thank you for your patience with me. Okay, and good luck on your final exam. I hope you do very well, each of you, so I can give the good grade for every student. All right. Okay. Thank you.